So today we are going to continue our discussion with valid and invalid arguments. Okay, let's start with a definition. An argument is a sequence of statements, and an argument form is a sequence of statement forms. All statements in an argument and all statement forms in an argument form, except for the final one, are called premises, or assumptions, or hypotheses. The final statement or statement form is called the conclusion. The symbol here therefore is normally placed just before the conclusion. To say that an argument form is valid means that no matter what particular statements are substituted for the statement variables in its premises, if the resulting premises are all true, then the conclusion is also true. To say that an argument is valid means that its form is valid. Let's see here. To test the argument for a form for validity, you identify the premises and conclusion of the argument form, construct a truth table showing the truth values of all the premises in the conclusion, and a row in the truth table in which all the premises are true are called critical rows. If there is a critical row in which the conclusion is false, then it is possible for an argument of the given form to have true premises and a false conclusion, and so the argument form is invalid. If the conclusion is in every critical row is true, then the argument form is valid. So let's look at an example. All right. Let's see here. If P, then Q or not R. If Q, then P and R. And therefore, if P, then R. Right? Yeah. Okay. Is that argument valid? It doesn't matter what the P, Q, and R stand for at this point, but is the argument being presented a valid argument? So we construct a truth table. We have P, Q, and R. So P, Q, and R, and we start with and let's see here. No. Going back and forth between this and digital logic can be challenging. Okay, those are all the possible truth values for P and R, P, Q, and R. Then we have not R. So we have not R. That's going to be false, true, false, true, false, true, false, true. All right. Now we have Q or not R, because we have Q or not R. So we do or not R, and Q or not R is true here, true here, false here, true, 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 false, and true. Yeah, true. So you just got a couple of falses in there, and the rest are true. And then we have P or and R. P and R. Well, it's going to be true here. False, true, false, and then false all the way down here because P is all false. Okay. Now, okay, that's the elements of the arguments are all represented. Now the premises are if P, then Q not R, or not R. So premise 1 is if P, if P, then Q or not R. So if P, then Q and or not R. So that would be true. True. False. True. And these are going to be true by default. Did I get that all right? Yeah. Yeah. Okay. Now the second premise is if Q, then P and R. All right. So premise 2, if Q, then P and R. So if Q and P, then P and R is true. P, then that's false. That's going to be true by default. That's going to be true by default. True and true. And true by default. All right. So those are these are the two premises. Everybody see how I got those? I had my back turned, so I haven't seen any looks of confusion or anything like that. So, but those are the first two premises, or the two premises. Now the conclusion, if P then R, which you only need to worry about the critical rows. The critical rows are here, here, here. Wait a minute. I got a couple wrong here. Oh, okay. Hold on. These are false because if P, no, that's true. This is false. These two are false because Q is true and P and R is false, so the premise 2 is false in those situations. So the critical rows are these rows here. So now we just evaluate the conclusion, if P then R, on those 3 rows. If P then R, true and true, that's true. This row here, true and false. That's false. And then false and false are true by default. So the conclusion is false in one of the critical rows. The premises are true, but the conclusion is false. Therefore, the argument is not valid. It is not a valid sequence of logic. So going back to this, not valid. But yeah. So you do it by constructing you determine the validity by constructing the truth table and looking at the critical rows for the premises, finding where they're all true, and comparing that to the conclusion and see if they're true for all the critical rows. These don't matter. But this makes it invalid. Now, an argument form that contains 2 premises and a conclusion is called a syllogism. Let me the 2 premises are called the major premise and the minor premise. And 2 famous forms of syllogism. One of them is called modus ponens, which is Latin, which I don't remember what it means. But if P, then Q, P, therefore Q. Now you can easily see that when you have the truth table for this, P, Q, P implies Q. You have true, true. If P then Q, then this is true, true, true. Oh no, this is false. True. And so if in your critical rows you have your critical row here, that's the only one, and the conclusion is true. Q is the conclusion, so this is a valid argument form. Another famous syllogism, modus tollens, again the Latin that I forget. You have to forgive me, it's been about 40 years since I took Latin. If P then Q, not Q, therefore not P. And to do the truth table for this, if P then Q is going to be true, false, true, true, and the conclusion, not P, is true here, and not Q is true here, so this is your critical row. This is your critical row because P implies Q is true, and not Q is true, and the conclusion is also true. Therefore, it is a valid or argument form. So these are little tools in your toolbox of manipulating and evaluating logical arguments. Let's see here. Let's see here. Let's give an example here. Let's see here. If there are more pigeons than there are pigeonholes, then at least 2 pigeons roost in the same hole. There are more pigeons than there are pigeonholes, therefore, at least 2 pigeons roost in the same hole. So, if P is equal to more pigeons than pigeonholes, and Q is 2 or more pigeons roost, you have the form if P then Q. P is true, therefore Q is true. So, yeah. That's modus ponens, demonstrating that valid argument form. So, additional valid argument forms, the rules of inference. We're going to go through several of these. Rules of inference. Okay. A rule of inference is a form of argument that is valid. They can make generalizations. So P is true, therefore P or Q is true. More generally, P or Q is also true for any statement Q. If P is true, we saw this in the logical equivalence. P is true is making that a tautology. Looking at a tautology, T or Q is true, is equivalent to a tautology. So P is true or any value, it doesn't matter what it is going to be true. That's generalization. Let me get rid of this. Specialization is next. P and Q, therefore P, or Q, or therefore Q. Specialization is for discarding extraneous information, focusing instead on the property that you are interested in. So, if P and Q is true, then both P and Q must both be true, therefore P is true. Or Q is true as well. So you can eliminate a variable in the process, a property. Elimination. P or Q, not Q, therefore P. This argument's form says that when you have only two possibilities and you can rule one out, then the other one must be the one that's true. P or Q. Q is not true, therefore P must be true. If P or Q is true. Let's see here. Transitivity. If P, then Q, and if Q, then R, therefore P implies R. Chains of if-then statements can be reduced to the first statement implying the last. It often happens that you know one thing or another is true. If you can show that in either case a certain conclusion follows, then the conclusion must also be true. Let's see here. Big example. Let's see here. Nice big example. You are about to leave for class in the morning and discover that you do not have your glasses. You know the following statements are true. I'm going to say RK is reading my notes in the kitchen. Okay. The glasses are in the kitchen. SB saw glasses at breakfast. RL reading my notes in living room. GC glasses on coffee table. Okay. So what this with those variables, represent is, if I was reading my class notes in the kitchen, then my glasses are on the kitchen table. If my glasses are on the kitchen table, then I saw them at breakfast. I did not see my glasses at breakfast. I was reading my class notes in the living room, or I was reading my class notes in the kitchen. If I was reading my class notes in the living room, then my glasses are on the coffee table. Where are the glasses? So, you sequence the sequence of steps to reach the answer. If RK, then GK. If GK, then SB. Therefore, if RK, SB. If RK, then SB. Not SB. Therefore, not RK. RL or RK. Not RK. Therefore, RL. If RL, then GC. RL, therefore GC. Now we'll go through this step by step. If you're reading in the kitchen, then the glasses are on the kitchen table, or in the kitchen. If the glasses are in the kitchen, then you saw them at breakfast. Therefore, if you were reading in the kitchen the night before, then you would have seen them at breakfast. Given that's by transitivity. RK, if you were reading in the kitchen and you saw them at breakfast, but you didn't see them at breakfast, therefore you weren't reading in the kitchen. By modus tollens. Valid argument. You were reading either in the living room or you were reading in the kitchen. You were not reading in the kitchen because of the conclusion here. Therefore, you were reading in the living room. By elimination. If you were reading in the living room, then the glasses are on the coffee table. You were reading in the living room because of the conclusion over here. Therefore, the glasses are on the coffee table by modus ponens. So the glasses are on the coffee table. You can derive logically using these rules conclusions. This is what we go through in our heads, reasoning things out. I'm sure you most, at least some of you got the fact that the glasses were on the coffee table before I got through all this. But this just mathematically formalizes that logic that we go through and eliminate possibilities and derive conclusions. So let's see here. Are people still writing on that one? No? Okay. Fallacies. Okay, a fallacy is an error in reasoning that results in an invalid argument. 3 common fallacies. Using ambiguous premises. Circular reasoning. And jumping to a conclusion. We can show that an argument is invalid by constructing a truth table. If there is a critical role that has a false conclusion, then the argument is invalid. Another way is to find an argument of the same form with true premises and a false conclusion. Let's see here. Some ways of forming invalid arguments. Also, did I? Yeah. All right. You have converse error. Where you say, if P then Q, Q, therefore P. Looks like modus ponens, but it is not. It is an invalid argument. Take for the following example. If Zeke is a cheater, then he sits in the back row. Zeke sits in the back row, therefore Zeke is a cheater. No, not so much. Doesn't work that quite that way. So this is like the converse of trying to use the converse of this to use modus ponens. That's why it's called converse error. Inverse error. If P then Q, not P, therefore not Q. Looks like modus tollens, but it is a invalid argument. Take for the example, if these 2 vertices are adjacent, then they do not have the same color. These two vertices are not adjacent, therefore these two vertices have the same color. See where that falls apart? Yeah. Not a valid argument. Let's see here. A valid argument, another type of invalid argument is a valid argument with a false premise. If a premise of an argument is false, then the argument is invalid. So, take the argument. If Canada is north of the United States, then the temperatures in Canada never rise above freezing. Canada is north of the United States, therefore the temperatures in Canada never rise above freezing. While the argument is in the proper modus ponens forms, it is not a sound argument because the first premise is false. Just because it's north of the United States doesn't mean the temperatures never rise above freezing in Canada. Yeah, it's a false premise, therefore it does not make a valid argument. An argument is called sound if and only if it is valid and all its premises are true. An argument that is not sound is called unsound. Just kind of a definition of terminology there. Contradictions and valid arguments. If you can show that a supposition that statement P is false leads logically to a contradiction, then you can conclude that P is true. Okay, so that show the following argument is valid. Let's see here, contradiction and valid argument. Let's see here. Let's see here. If P then C, where C is a contradiction, therefore P. If not P, I'm sorry. Not P, then C for a contradiction. Therefore, Therefore, P. Okay. So, look at the truth table for that. P, not P. And conclusion is going to be true, false, false, true. And this is always false. So, not P implies contradiction is only true when not P is false and it's true by default. That makes this one false. True and false doesn't work. And P is true. The conclusion is true when the critical row is true, because the conclusion is just P. So That's how you can use a contradiction to show the truth of a statement. Let's see here. On one of the slides, in this section, there's a summary of rules of inference. I recommend you download the slides. I don't remember what section it is, or what slide it is, but it's I think it's 2.3. It is 2.3. Yeah. But it has a summary of the rules of inference. Elimination, generalization, specialization. We didn't do division into cases. Let's see here. Division into cases. If P, then R. I think. It's here. Yeah. Oh, starts with P and Q. And Q. P, Q then R. Therefore, R. You can show that the result is the conclusion is true by having it dependent on multiple. P, Q. I messed that up. That's P or Q. Yeah. If P or Q is true, and P implies R and Q implies R, they both imply R, therefore R must also be true. Because one of, in order for this to be true, but one or the other of P or Q must be true. So these are not true by default, or one of them at least is not true by default. And therefore, the result R is must also be true. All right. Now for a section that I'm not too fond of. It's not, this is the wrong class for this, but let's see here. Do we have time to cover all this? Let's see here. I think we'll call it a day. I don't think we have enough time to go through this whole section. We'll look at on Tuesday the application of logic in logic circuits, in Boolean logic circuits. And let me see here. And that will bring us to the close of chapter 2. And so next Thursday, we will have a test on chapter 1 and 2. So next Tuesday, we'll finish up chapter 2. Thursday, we'll have the test on 1 and 2, cumulative. So that'll be it for the day. Have a good day.